the second page, starting with example 3 of the notes from sections 4.1 and 4.3. This is on derivatives in different contexts. We've talked about like velocity and acceleration and things like that, but let's talk about them now in other real world contexts. So this example, I wanted to use Desmos on this, so I switched over to a second screen so that I can have the split screen here. Because I wanted to show you all of the ways that Desmos can kind of help you with a question like this one. So the store is having a 12-hour sale. The number of shoppers who have entered the store. Okay, so a couple important things here. First of all, this is a number function. And I told you that's the first thing you should always identify. Are we talking about a number or a rate? And then also, just because I know it's going to be important later on, I want to point out this is the shoppers who have entered the store. So the number who have walked through the door, okay, after the sale begins. So I'm going to just start by graphing this thing. Desmos actually would do an E of t, like if you had typed it in the way it's written in your notes. But I found that it's a little bit finicky about doing derivatives when you use a variable other than x. There's probably a way to make it work, but for the time being, I think I'm just going to use x's here, just so we don't mess anything up. Okay, now this function actually looks different than this. You have to really adjust your window here. So it told us that this is for the window from 0 to 12 hours. So I'm going to make my x-axis go 0 to 12. Okay. But also this graph goes up way higher than what you can see here. I have found that I typically have to make my y-axis go up to like 2,000. Right? A lot of people coming into this store. And let me pull that up so it's in the window here so we can see the whole thing. And here's our function. I honestly don't know if we need the picture of the graph to be able to answer these questions, but helpful for a visual. So the next question says, at what rate are the shoppers entering the store? And so this is where I want you to think about, how do you go from a number to a rate? Okay, that's where the derivative comes in, right? So what I really want here, oh, sorry, dropped my pen. What I really want here is the derivative of e at 5 hours. So I'm going to say e prime of 5 is what I'm looking to evaluate. Desmos can do that for me. I can just ask Desmos, hey, what is e prime of 5? It tells me it's 200. That's my answer. Now, this is a rate, so let's make sure we label it appropriately. At what rate are shoppers entering the store? This would be 200 shoppers per, my time is in hours, right? Shoppers per hour. Okay, next one wants me to evaluate a second derivative, e double prime of 3. It tells me that that is 0.4. Okay, so what this means in the context of the situation, I guess let's jot this down. So e double prime of 3 is 0.4. Okay. If we're talking about a second derivative, this is the rate that the rate is changing. Okay. So I would say that the rate, here's another long writing one. Feel free to zoom ahead if you need to. The rate that the shoppers, oh, I left the H out of shoppers, are entering the store just to clarify here before I continue, this is not the rate that they're entering the store. This up here was a rate that they were entering the store. This is the rate that the rate is increasing, right? So I would say the rate that the shoppers are entering the store is increasing. That's an important word. By 0.4 shoppers per hour, right? That's what a second derivative is telling us, is how much is the derivative changing by. So this is the derivative, right, per hour. Okay, so this next one. Suppose the number of shoppers who have exited the store T hours after the sale began is modeled by this function. And then there are 15 customers in the store at the start. Okay, so I'm just going to kind of write for you my thinking here, and then we'll fill in some functions. That if I want to know the total number of shoppers, that's going to start, oh, I'm writing this in the wrong spot, so sorry. The number of shoppers starts with these 15 people, right? There were 15 customers in the store at the time the sale began. So we started with these 15 people. And then we had a bunch of people enter the store, right? That was that original E of t function. So I want to add the people who enter and subtract the people who exit. Now, that's a really informal thing. That's kind of what's going on inside my brain right now. Now let's write it in function words, right? So I'm going to make a new function with a new letter. I'm going to say s of t. The beautiful thing about calculus is once a function has a name, you're allowed to just refer to it by name. So I'm going to take my 15 people, and then to say how many people have entered the store, I'm just going to use the name of this function, the E of t. Where am I pointing? Here we go. E of t. So plus E of t. And then subtract the shoppers who have exited the store. So that's x of t. And that's it. That's my answer, right? This is my new function that tells me at any given time how many people are actually in the store right now. Now I'm going to graph this function because I think we're going to need it in a second. Let's get rid of these guys. So I'm going to make a new function, s of x. Again, have to use x instead of t. Oh, and you know what? I never put in, before I do this, I need that x of t function in here. Desmos is not going to like me using x as the name of the function, so I'm just going to use f. Okay, f of x equals 0.5t. I know, nope, 0.5x, sorry. I know that this looks like a straight horizontal line. I promise you that it's not. It's just because of the scale of the graph. If I were to like put this back to how it started, you can see that that line is actually diagonal, but it's just because of how big I've made my y-axis that it looks like it's flat. Okay, because 0.5 is not a very big slope. So, and then what I want is a function that subtracts the two of those things. So my s of x function is going to be 15 plus e of x minus f of x. That black function looks really close to the red function, right? But that's just because this is a really tiny amount of people that are leaving. This is actually probably a pretty unrealistic rate that people are leaving. This is like one person leaving every 2 hours, okay? So you can see they're not exactly right on top of each other if we zoom in, but that black function tells me how many people are in the store at any given time, okay? Well, I guess I can click here and show you that this is the 15 people that start off inside the store, right? And then it grows because the number of shoppers is growing. Okay, I wanted that graph in here because I'm going to need it to answer this next question, or maybe not the graph, but I'm going to need Desmos to do it. We want to know if the number of people in the store, so that's the s of x function, right? Number of people in the store is increasing or decreasing at 3 hours. Anytime I ask you that question about increasing or decreasing, that is a derivative question, okay? So what I really need now is s prime of 3. And I can do that now that I have this function typed into Desmos. So I'm going to just ask it, what is s prime of 3? And it does all the dirty work for you. Now, I actually don't care about that number at all. I mean, what that's telling me is like how fast the number of people inside the store is changing by at 3 hours, okay? But I can just say s prime of 3 is positive, so that means that this thing is increasing. And really, this is all I need for my justification. You don't have to be real wordy about it. We found the derivative, we showed that it's positive, okay? We don't even have to write down what the actual derivative is. So that's that. I'm going to jump through example 4 real quick, even though example 4 is very much review of stuff you've seen before. But it's a good time to review it. We've got another function that's given to you in a table, okay? And w of t is talking about like the temperature, right? So when I ask you W prime of 15, what I'm asking you is how is the water temperature changing when the time is 15? Okay, sorry, I'm trying to move my camera around here for you a little bit. Okay. So we don't have enough information. Like this, if I were to graph this, this would just be a bunch of separate dots. That's not nearly enough to figure out what an actual derivative is. So we have to estimate it. Like there's a reason that this says we're estimating, okay? It's because we're doing a fake derivative here. If I want to look at 15 minutes, that's somewhere between the 10 and the 20, which means I'm going to do an average rate of change between these two things. So I'm going to say W prime of 15 is about equal to 79 minus 90 over 20 minus 10. Let's see, I think that's negative 11 over 10, which is negative 1.1. It didn't ask me to label it, but you always should. So negative 1.1 degree per minute would be my label there. Okay, I guess it asked me in the next question to label using correct units, so I'm going to need the units there anyway. But what does this answer mean? We want to talk about it. So I know this is an average rate of change, the calculation we did, but we were using it to estimate a derivative. So remember, this is where we fake it and we pretend that this thing is a derivative. Okay, we talk about it like it's a derivative. So I'm going to say at 15 minutes, what is this function talking about? The temperature, right? Is, well, that's negative, so decreasing by how much? 1.1 degree per minute. And last question, is there a time between 0 and 30? So we're looking on this whole interval here, between 0 and 30, where the temperature has to equal 85 degrees exactly. Now I don't see 85 degrees in the table somewhere, okay? This is an IBT question, and hopefully you recognize it as an IBT question. Remember, IBT tells us that things exist, guarantees that things exist on a particular interval. So let's think about our condition here. I know 85 falls in this range here, between the 90 and the 79, okay? We also could say, by the way, that it falls between the 104 and the 72, but this gives us a tighter range to work with, so we can be a little more specific. Either one of those answers would be okay. Okay, so here's how I'm going to justify this. I'm going to say yes, because, and then we need to state our conditions for the IBT. First condition is that this function is continuous, and I want you to think about why you know that this function is continuous. It's because this says that this function is twice differentiable. That just means I can take a derivative twice, but if I can take a derivative, then I have a differentiable function. So I'm going to say yes, because w of t is differentiable, so it is also continuous. Remember, you always want to establish that link between differentiability and continuity. And the second condition, and, is that the number we care about lives in this interval. So I'm going to say, and it actually, this is the smaller run, right? So I'm going to say W of 20 is less than 85, which is less than W of 10. So we actually know that it has to be exactly 85, somewhere between 20 and 10, which is like a smaller subset of this interval, so that's my answer. Okay, so the two things I'm looking for here in an answer, I guess three things. One would be answering the question, right? Yes or no. We have to state that it's continuous, but make sure you state that it's continuous, like that you know it's continuous because it's differentiable. and then tell me that the number we care about lives on some interval within the table. Okay, I think you've got the idea here. This is just identifying what derivatives mean, what they tell us in these real world contexts. You got a little bit of homework on this tonight, but you'll definitely be seeing these problems as the year continues. So have a great night.